Okay, so let's now move on to the thermal boundary layer. Okay, so again, let's draw first our pipe for so that we can have our pipe condition of internal flow. Okay, so same with the last time, of course, before the the fluid enters into the pipe, the temperature profile will looks like this, right? Okay. So for thermal consideration, let us consider this fluid stream at some mean temperature. Say it has a mean temperature of Tm, where this mean temperature of the fluid is lesser than the temperature of this pipe surface. So this means that the pipe is hotter than the fluid that is going into the system. So as the fluid enters this pipe or this tube at a uniform temperature, then we can see a thermal boundary layer begins to develop from the circumference and merging at the center line at some distance. Okay, and this distance is called the thermal entrance region. Okay, and let's draw this. Say this is our center line. Okay, so let me draw the once again the flow regime. It will looks like this. Right? Okay. So from here to here, here, okay. We have here our um, um, the temperature boundary layer from here to here. And if we're gonna see what happens to the profile is that from say for example we examine at this point, then we can have a we can see that the profile will somewhat looks like this, since this surface is hotter. So the fluid layer has a what do you call this, higher temperature. Then it will pass the it will what they call it, the first layer will exchange energy to another layer, so that your temperature profile will looks like this. Okay, and then it somewhat became flat here, and then once again have this layer. So all in all, we can have a temperature layer that looks like this here, and then flat, and then curve. Okay, so that is in a region, that is the temperature profile in a region called the thermal entrance region. Okay. Okay. And while the we have now our fully developed region, the temperature profile will somewhat looks like this. So the fluid layer that is in contact with the direct contact with the pipe surface will have the um, highest temperature, and will create a temperature profile that is oh, I mean that is also a parabolic type. Okay, so ganyan. Okay. Okay. Ayan. So again, let us review. If we have a condition that our mean temperature of this fluid stream is lesser than the temperature of the surface, meaning our pipe or tube is hotter compared to our fluid, then as this fluid enters the tube at a uniform temperature, a thermal boundary layer begins to develop from the circumference, so this one. Okay, and merging at the center line is merged at the center line at some distance called this thermal entrance. This one at the thermal entrance region. Okay, and beyond this thermal entrance region nga is the what we call the fully developed region. So depending upon the surface condition, a temperature um, temperature of the surface is constant, or a uniform heat flux is constant at a different temperature profile. Different temperature profile will be formed. So for both surface condition, however, the amount at which fluid temperatures exceed the entrance temperature increases with increasing x distance, right? So for laminar flow, um, the thermal entry length may be expressed as xf dt all over d. So this is for laminar flow, and that is approximately equal to 0.05 Reynolds number times the Prandtl number. Okay, and for turbulence, um, it's just the same with the velocity boundary layer, that is xfd all over d. Turbulent is approximately equal to 10. Okay, so that's all for the thermal boundary layer and for the velocity boundary layer of the internal flows.